0.4439 kilonewton. And that is your first RB. And what else we need to do? The next step, you have to determine the next member will be CD. Correct? Can I? Or should I? Now I should move there to. Right, so now I have to look for member CD, right? So CD, I will draw it here. This is C and this is D. So what are the moments that I need to put in? So what is the moment for C? What's the value? What is the value that I should use? The 4101, right? What is the direction? Forwards or anti-clockwise? Anti, because it's negative. So you know that this is going to be 0.4101. Right, and how about moment at D? Anti-clockwise as well, right? So it's going to be 0.2041 in this case. And after that, you then have to put in what is your RC and what is your RD you need to determine. Right? So for this case, your interest is to get RC. Because RC is actually along the horizontal direction at C. So for that, you can then take summation of moment about D equals to 0. Right? So for moment about D equals to 0, and for this case, well, if you were to take clockwise as positive again, right? So what we're getting, you know, there's actually minus 0.2041 minus 0.4104, and C, right? C is going to induce a clockwise moment. That is equals to plus. Again, the distance is how many? It's 1, right? So it's actually 1 multiplied by RC equals to 0. So by working out, your RC is equals to 0.6142 kilonewton. So what is your popping force? Right. So in terms of so your popping force, right? Of course, it will be the summation of forces, right? In the horizontal direction, in the of course in the horizontal direction, right now. So what are they? It means it becomes 0.6142 plus 0.4439. That will give you 1.058 kilonewton. Right. So this is actually the popping force value that you should obtain. Sorry? Yeah, okay, right. So let me come to that, right? Why not? Do you want to come out and try? You should actually try it, then you'll be able to get it more familiar, right? Okay, good. So let me just rub this off. Is it better for me to draw here or go the other side? Okay, I'll just alternate. Are you okay? Done with this? I'll just draw it off, and then I'm going to draw the bending moment diagram. Right? Alright, so now we are going to draw the bending moment diagram. So first thing is that, depending on how you see, of course you can actually draw the bending moment diagram of the entire frame, or you can actually break it down individually to draw, right? So what I'll do is that let me first start off with AB. Right? For AB, I mean my approach is that I think I can actually just bring it down. So this becomes AB. Right? Because what I'm trying to say is so that if I bring it down to horizontal, I'm able to draw the bending moment diagram clearer. Right? So AB, what are the moments acting in AB? So you know already for AB, it's going to be in a clockwise direction, right? That means 0.1844, and you know that the moment is going to be 0.3705, right? So now with that, alright, so this case is going to be hogging or sagging. So it's sagging, right? So because it's sagging, and this side it's going to be hogging, right? Yeah. So from there you will know the shape anyway. Right now, so as I said already for, this one is EP. This one is correct. Sagging, right? So for sagging, right, what will we have? Yeah.
这个跟那个一模一样的，好像有点不公平。这个跟那个一样的，它比较，这个比较容易，对，这样有点不公平。对这个 batch 的一样是4分，那个
Alright, so sagging is okay, sorry, so this is sagging, right? This is sagging, so it should be positive. So for this, what you do is that you take it here, which is so you know that this is going to be here. Energy is positive 0.1844, and after that here, because it's hogging, you know that it's actually negative. So from there, this is going to be minus 0.3705. So from there, you are able to actually draw this. Then this is going to be the bending moment diagram for AB. Right? So for that case, you can actually put it here. Of course, you can actually, if you want to do it, you can actually move it over there to complete it. And so I'm just going to draw everything in terms of horizontal. And after that, how about BC? How about BC? What is the moment? For moment BC is going to be, the moment here is going to be 0.3705 because it's anti-clockwise, and for moment where C is going to be 0.4101, right? So for this case, how's it going to be like? So everything is hogging, right now. So if everything is hogging, right, hogging, right? Right, because it's pushing upwards. So for this case, you need to actually draw from here, and you know that because it's hogging, it's going to be negative. So from here, you will start off with, this one is actually minus 0.3705, right? And after that, this point is going to be minus 0.4101, right? So how is it going to be? So you know that if everything is going to be hogging, you roughly know the shape has to be, it's going to be a parabolic shape, right? It's going to turn this way and go up. Right, so this is going to be the bending moment diagram for this kind of loading condition, where the moment is in this. Alright, Good. So now after that, this is going to be C and D. So CD, how do you draw? What is the bending moment? The bending moment over here is 0.4101, and this is going to be 0.2041. And with that, how does it look like? Right now, this one is this one is going down, right? So for this case, you know that it is hogging and this is sagging. And by doing that, you know that this has to be, because sagging, so it's positive, and this is 0.2041. And this is hogging, and it's negative, so it has to be minus 0.4104. And with that, you will be able to join from point A to point B, so from point C to point D, and this is the bending moment diagram. So with that, you complete the bending moment diagram for the structure A, B, C, D. Yes.
Calculate the maximum bending by
Here is it?
Yes.
Alright, so the question is that do we have to calculate this one? Yes, you have to. No, I mean, okay, it depends. If the question asks you to determine the maximum value, you then have to determine. If not, right, you don't need to. Right, so look at the question to see whether is it just asking you to determine the bending moment. Because definitely have to be the shape.
How do you calculate?
How do you do that? How do you determine this particular point? Oh, is it? Sorry? WL over A. Why is it WL over A? You mean WL over the formula? Is that the formula? No. Okay, the only example I think is asked for is actually in example page 8, right? Is it the example in page 8? You need to determine exactly where is it. So the thing is that, well, you need to recall where does this is bending moment diagram, right? This is actually bending moment diagram, right? Do you recall? Because you know, if you learn how to draw bending moment diagram, you need to learn also how to draw shear force diagram. So what is the relationship between shear force and bending moment diagrams? Yeah, so area under shear force actually becomes the change in the moment, right now. But also there's another relationship. The maximum point, right, is actually where shear force equals to 0. Right? At the point where shear force equals to 0, that's where your maximum bending moment is going to occur. That is actually the rule, because by integration you know that is actually, because you know, right, the slope that you integrate, right, becomes the shear force. Right now. So this is the slope, and when you integrate at this point here, what is the gradient? The gradient is 0. So actually dm over dz is equals to the shear force. So once at this point, it corresponds to the shear force equals to 0. So you need to go and find out what is the value of the shear force where at the point where shear force is equal to 0. Right now. So how do you determine that? If you refer back to the example, right? The example in page 8. So what you need to do now is that you have to go and determine what is the shear force at RB and at RC. Right? You need to go and determine the shear force at RB and RC. And by doing that, right, you will know that one of the value, okay, assuming if I'm actually able to obtain this, right, the value of the shear force, because this is a uniformly distributed load, the shear force would definitely start from 1 from positive and then probably 1 from to negative value. Assuming that if you determine this value is equals to, let's say it's if it's minus 3.5, let's say, and this is equals to 4.5, right? So this is going to be 3.5 and this is 4.5. Are you able to find out exactly at which point the shear force becomes 0? You should be able to, because you know what is this distance, right? What is this distance? This distance is 1.5 meters. Right now, so this distance is actually 1.5 meters. Right? So you know that. So you know what is this gradient? 1.5 ma? No, sorry. So what's the distance? I think it should be given, right? 2 meters. Alright, okay, can. So this is 2 meters. So if you know this is 2 meters, you will be able to find the gradient for this one, right? So this gradient would just be equals to, of course it's 4.5 minus 3.5, be, I think it's 8 went up. So the gradient is actually 8 divided by 2. That will be actually equals 4. Right? So where is this point at? Where this point becomes 0? Right, is this gradient equals to 4, right? Because it's 3.5.
Negative 4.
I mean negative 4 lah. Okay, yes, negative 4. The gradient is negative. If the gradient is negative 4, right? And can anybody work out for me what is this distance? What is this x? Yeah, then I can work out that what is this distance now? By triangle or by gradient? Now I'm waiting for, at least you show me the working how you get this distance. How? Cannot figure out?
0.875.
Huh? 0.875 is it? So I trust. So how do you get 0.875? Because this is the gradient, right? Because basically you know that if this gradient equals 4, right? So that means this is the triangle, this is 3.5, this is x, this has to be 4, right? So in order for the gradient, it means 3.5 divided by x has to be equal to 4. Right? This is gradient. So your x, I suppose, is 3.5 divided by 4. You get that value here. Right now. So you are able to determine this distance already. And after that, what next? What's next? Huh? Can I round this off? So if you refer to the notes again, you then have to consider this member. What is this member? This member, you need to take it such a way that it is going to be, alright, how you need to determine the moment over here, right? You then have to actually determine, now this is my member, I need to start from BC. For this case, I need to do a cut, I need to do a method of section. If I do a section over here where this is actually E, what I'm going to do is that I'm able to draw a element, right? Where this is B, and with that, assuming that because for this case, the reaction force RB is equals to minus 3.5, right? And because over here there's a uniformly distributed load. Remember? So this is a uniformly distributed load right now. But this uniformly distributed load you can actually replace by a point load. What is this uniformly distributed load? It's actually 1.5 kilonewton per meter right now. If you replace this with the point load, so what is this point load going to be? Sorry? So what is this point load going to be? Sorry, okay, of course, when you do a cut here, this is going to be x. This is going to be x. So what is the point load that you should replace with? What's the point load? Times how many? Times how many? By 4. It's just x. Because this is the distance x and this is 1.5 kilonewton per meter. So of course this force will just be 1.5 multiplied by x. Sorry, multiplied by x. Now because this is uniformly distributed per meter, right? So the distance is x, so of course the force is 1.5x. That is the point load that you replace. Now after that, you then need to know the distance. Right now. So what is let me see. Okay, so what is this distance? What is this distance? Half, right? So it's just going to be x minus half. Right now. So after that, so these are all the kind of distances you put in. Don't forget, at the point where you do a cut, right? What do you have to introduce? What do you have to introduce here? You need to introduce there's a V, shear force, right? And there's also going to be a moment that's actually being introduced at every cut section. Then you should recall your mechanics of materials. Huh? Alright, so with that, you are ready to actually take rotational equilibrium. Assuming if you take rotational equilibrium about, okay, wait. So for this case, what you need to do is that you have to assume you have to take summation of forces in the y direction equals to 0 first. Because you need to solve for your v. Right? So this is your v. So what is your v going to be? Your v is downward force, right? That is to say v plus 1.5x is equals to, sorry, this is not, so this is, okay, assuming this is equals to 3.5, right? So your v is equals to 3.5 minus 1.5x, right? So now you take summation moment of force equals y equals 0. Then this means that you need to take summation of moment about, assuming you take about b equals to 0, right? You take equal to 0. So if you consider all the clockwise, all the clockwise moment, no, for this case, okay, correct. Clockwise, okay. So if you consider the clockwise to be positive, right? That is to say, if I take about b, that means 1.5x, right? This is the point load you have replaced. What is the moment arm? It's x over 2 multiplied by x over 2, right? Plus your v multiplied by the distance x. This is the moment arm, and that is equals to, okay, of course, minus m. Minus m equals to 0. Right now, so if you are to rearrange, your m is equals to, you bring over, you will be 1.5 divided by 2, okay, 0.75, 0.5 x squared plus, what is your v? Your v is 3.5 minus 1.5 x multiplied by x. Right, so okay, anyway, what you do is that you are able to expand this thing out, where you get the equation of, in terms of x squared and x. Right now, so for example, if you are able to, let me see, this is equals to 0.75 x squared, and this is minus 1.5 x squared, right? And plus 3.5x. Right, so eventually m is equals to minus 0.75 x squared plus 3.5x. Agree? So this is by my method of section, you got it, your m. So effectively, what is are you able to find out what is the value here now? How? So because this, your moment is actually minus 0.75x plus 3.5x, right now, and you determine where is your x value. Your x value is equals to, how many here? What is this value? 3.5 divided by 4, what is that? 3.5 divided by 4?
0.875.
0.875. Alright? So you know that where is the point where your moment is actually maximum, because that corresponds to your shear force equals to 0. So as shear force equals to 0 is where the distance where x equals to 0.875. So with that, you substitute x equals to 0.875 into the moment equation that you have actually obtained. Then you can determine what is this value n here. Right, so you really have to go and revise your example in page 8, the solution. I mean, of course, you have to, of course, if the question asks for maximum moment, then you have to go through all the steps to determine what is that maximum. Yeah, the span distance is, okay, what is that span distance? It's x. Yeah, it's the x value. So the span distance is that you need to tell me exactly at which point is the maximum spanning moment is going to occur. I know. So for this case, assuming that if x is 0.875, that means is that it's somewhere along here, 0.875, the maximum moment actually occurs there.
So that's the maximum span.
Huh?
That's considered maximum span.
No, I don't think it's maximum. I think it's the span. It's not the maximum span, right? Yeah.
What is the maximum span is the bell slightly beside the span distance, right? According to
Sorry, according to?
the what is it called?
Yeah, okay.
Yeah. You say the span distance is the maximum span slightly different. It's beside.
Maximum span in the. Yeah, okay, correct. See, the maximum, so you don't know whether the maximum is going to be a center or not. You cannot assume the maximum is center, right? By looking at that, you know that the maximum cannot be a center, right? Because these two values are different, man. Unless these two values are the same, you know that the curve is symmetric, then it's at the center. But because these two are not symmetric, the maximum moment cannot be at the center. Right, so you have to actually determine. So what I'm saying is that if maybe this is not at the center, so but at center there might be a value of n over here. Right, so there can be a lot of things that asking you to determine. They ask you at the center span, right? What is the bending moment? You still have to work this out. To substitute x equals to 1 into this equation to find out the moment at this point. Right? Not. This is the point where if I want to ask you what is the bending moment at the center of the span. But if I want to ask you for the maximum bending moment, you don't know whether the bending moment might be at the center. You have to determine where the shear force is equal to 0. That is the span where the bending moment is maximum. So again, you see, this is really to assume, not say assume that because that you already have the background of the basic of mechanics of materials. Right, so you should be familiar with drawing the bending moment diagram, shear force diagram, and also this is actually to determine the bending moment by the analytical approach. Because by analytical approach, then you need to actually do all the method of section to determine the various equations for V and M. Oh yeah, good question. I don't know.
Because I see you go through very fast, so like.
No. I go through wow, you're good, huh? I go through fast because I know that your notes is there, so I'm just going to go through it. So this is the steps you have to actually follow. So the example 8, the example in page 8 actually depicts all the steps for determining the maximum movement. You have the trend, right? You can actually go and take a look. And that is the trend. I can only tell you up to 2016. 2017, I don't know. Alright, so the thing is that Dr. Kekili did mention to you, right? Dr. Christopher York is not able to make it. Actually, there is week 11 for you, yeah. So he's not able to make it. So you don't have a chance to ask him. But anyway, what I can just kind of like yeah. You go and observe all the previous past year papers trends. Huh? How many papers you have?
But the fatigue trend, right? The fatigue trend, like fluctuating and
yeah, but you have to go and catch it, right? How constant? I think sometimes can be constant, but it also varies a bit, you know. Alright, I'm not in a position to tell you, but it's for you to go and observe what the trends. Just get yourself.
but very long never vary already.
Last year just vary, right? Last year. But anyway, I can say that you can look at all the past year's questions, the pattern doesn't deviate too much, right? Yeah. Okay, what else? What other questions? I know the tricky part will be true. At this drawing of a bending moment diagram, you must know how to draw the bending moment diagram, right? And how do you determine, of course, the maximum point here and there, and also the popping force. Yeah, correct. These are the essential ones. All right. What else? Yes. Oh, what is this? This one is for example of for past year paper. This is from 2016. This is last year, is it? Okay. Right. So, yeah, how do you do it? Okay. Yeah. Oh yeah, can. I think that's what you do. Yeah, basically you're taking a ratio. Yeah, correct. Oh no. Well, I mean, this is how I do. It's the same thing. It's the same. I can let you know what is the answer. What do you get? Alright, so what do you get? Yeah, okay, around, I got 20.4. Yes, so what your distance is what, 1.7 actually from B, is it? Yeah, correct. So our bottom is actually 2.23 from A, yeah. So correct. Right? Yes. Huh? Yeah, I can. Okay, sure, understand. So I'm just saying that whether do you have any other general questions? If not, of course, just take individual questions lah. Yeah. All right. So if not, then I think we can take a short break here. All right. So I think that's kind of like our end of the formal session. But if you want to stay back, I can actually address some of the questions that you have. All right. Yeah. Let me just go to him first. It's the one that uploaded, is it? The one that I sent you all, is it?